Are we ready? Okay. Okay. Good afternoon, everyone. It's my pleasure to introduce the colloquium speaker today, Professor Jason Jones. He's one of our own, so he's local. So he's an associate professor at the College of Optical Sciences. So he received his bachelor degree from Bethel College in 1994. I think it's a small but very good college, right? Which has produced quite a few outstanding physicists that I've seen. Oh, so who's from Bethel College here? Okay, one.
Two.
Two? Okay, so two. So I think that must be a very good place. So he got his PhD from University of New Mexico in 2001, and then he worked at GILA until 2006. Here he got the National Research Council Postdoctoral Award, which is a very good award. And then he joined our college in August 2006, and he has been with us ever since. So his research interests include optical physics, high resolution and ultra-sensitive laser spectroscopy, laser cooling and trapping, optical frequency metrology utilizing femtosecond frequency combs, nonlinear optics, and ultrafast optics. So his current research involves the extension of the femtosecond frequency comb into the extreme-ultraviolet using intracavity high-harmonic generation. So he has over 80 combined journal and conference publications and 2 patents. So he is the recipient of the NSF Career Award, which is a very prestigious award, and the DARPA Young Faculty Award, which is a very good award as well. So he's a member of the American Physical Society and the Optical Society of America. So he's going to talk to us about extreme UV frequency combs based on intracavity high harmonic generation today.
Okay, thanks. Right. All right, great, thanks. Yeah, so we've had some very nice talks already this semester in our colloquium series about these frequency combs. So I think a lot of you are familiar with them, and you're probably familiar with pictures like this, usually accompanied by these talks, right, where we have a very broad supercontinuum of light that can now fairly easily be generated across the ultraviolet and the visible portions of the spectrum. And it's very coherent light. And if you zoomed in very closely and looked at that with a very high spectral resolution, you'd see individual frequency components, the so-called teeth of the frequency cone. Okay? And so what I want to talk to you about is one of the projects in our group, which has been ongoing for a while, which is to try and upconvert this femtosecond frequency cone into the extreme ultraviolet, or the vacuum ultraviolet, below 200 nanometers or so. And have a number of collaborators on this project. Primarily Professor Ewan Wright, who's been working with us on a lot of the simulations that we use in these experiments. And the graduate students in my group, recent group, are here. Primarily David Carlson and Sung-Han Wu have been doing the experiments that I'll be talking about today. We've also been jointly working, along with Professor White, with Gregory Jacob and John Mangeli, who have gotten master's degrees, and they've worked on some of the simulations in these experiments. And it's supported by the Air Force, NSF, and TRIF. So just a little overview of what we'll try and get through. First of all, I want to talk about 2 fields that in the past, before the turn of the century, used very different experimental tools and techniques. And there's really very little overlap between these fields, precision spectroscopy and ultrafast science. And so I want to just give a little bit of a brief overview of those fields and how the development of the frequency comb techniques have really made these 2 fields overlap in a very close way and linked them very closely. So with that sort of background, then I'll go on to talk about how we generate these frequency combs in extreme ultraviolet, which is through this process of high harmonic generation. And what we do is we do high harmonic generation inside an enhancement cavity for very short pulses. So we call this intracavity high harmonic generation. I'll talk about how it's different than, or what some of the differences are between just normal high harmonic generation. And then I'll go on to talk about sort of a novel technique that we've developed to make really precise time-resolved measurements of extreme optical nonlinearities like ionization using the high sensitivity of these enhancement cavities. And then finally, I'll talk about what we've been working towards the whole time is to do direct frequency comb spectroscopy, the vacuum ultraviolet and extreme ultraviolet, and where we are in that. Precision spectroscopy for a long time, of course, has been used to really look and unveil the quantum world, right? Going back to the days of Newton, who showed us how to use dispersive optics to analyze the content of light, along with Fraunhofer, who first discovered these so-called Fraunhofer lines, absorption lines in the solar spectrum, due to the discrete energy levels of atoms and molecules. And with the Bohr model of the hydrogen atom, precision spectroscopy for fundamental science really took off because very careful measurements of these atomic and molecular transitions could be used to test the developing theories of quantum mechanics at the beginning of the 19th century. This type of spectroscopy, of course, is limited to a resolution of about a part in 10 to the 7th, just due to the dispersion of the spectrometers. But with the development of lasers and masers in the 1950s and 60s, the spectral resolution dramatically increased, orders of magnitude, because now you could generate highly coherent monochromatic light sources that you could tune across these transitions in atoms and molecules. So now you could very precisely probe the atomic transitions in hydrogen, for example, and other simple systems. And this enables people to do very stringent tests of some of the fundamental science, continuing on testing quantum mechanics, for example, by looking at the Lamb shift in different systems, which test quantum electrodynamics. And really careful measurements of the hydrogen atom lead to better defined values for fundamental constants like the Rydberg constant or the fine structure constant. All these things that affect the energy levels of the atoms can now be more precisely measured and tested. And people look now for things that seem crazy sometimes that when you first hear about them, like temporal variations of the fine structure constant. Do these things change over large time scales or in different spatial directions? Right? By carefully monitoring these transition frequencies, it's possible to test and monitor these fundamental values. So what's the state of the art today in this area? In terms of the laser technology, it's actually quite amazing. These days, one can take two highly stabilized lasers, as demonstrated just a few years ago. You lock them to a reference cavity, but they're two independent laser systems. And you can beat these two optical frequencies together on a photodiode, and you can generate a photocurrent that oscillates sinusoidally at the difference frequency between those two. And there's no phase perturbations in this sinusoidal signal on the time scale of several seconds. Right? So this is extremely coherent light. These are oscillating at 400 terahertz without any cycle slips coming out of the laser. So this corresponds to line widths on the order of 40 millihertz, extremely stable lasers. And these can be used to probe very, very narrow transitions. In fact, really limited by the ability to hold the atoms in place and get rid of systematic line broadening effects of the atoms, not as limited by the laser sources anymore in terms of the spectral resolution. So here's an example of a strontium transition that was slowly scanned with one of these lasers. It shows a line width on the order of a few hertz. Right? Extremely high Q for the transition. And they use these type of systems for developing next generation atomic clocks based on optical transitions. So now let's talk a little bit. So moving from ultrastable lasers and precision spectroscopy, another field developed, of course, with this laser technology that utilized very short pulses. So rather than developing sources that had very long coherence lengths in time, where the carrier frequency in the visible maybe has a period of around 2 femtoseconds, these days it's possible to generate pulses that last only a few optical cycles. So that's around 4 or 5 femtoseconds. You can argue whether it's 4.2, 4.3. But it's in that ballpark. They can make very, very short femtosecond pulses directly from the laser oscillator. And these have been used from the 70s and before for this field of ultrafast science to probe electronic and nuclear motion in atoms and molecules on femtosecond timescales. The field was originally called femtochemistry. Nobel Prize awarded in 1999 for this, being able to excite a molecule into a vibrational state, watch that wave packet evolve and decay, and not only probe those things, but also to control them, where you can excite a nuclear wave packet of molecule up to some excited state where it's oscillating. And the wave packet moves back and forth, and depending on when the second short pulse comes, you can either excite it into the ground state of a molecular ion or dump it back into the ground state. So probing and controlling motion on these femtosecond timescales using very, very short, highly specialized tools, these very short pulse laser systems. We had a very nice colloquium talk by Arvinder Sandhu just a few weeks ago on this field of attosecond science. So these two communities utilize very different tools, right? One wants a very monochromatic, highly coherent laser source so that in the frequency domain you have a very high spectral resolution, narrow frequency. And the other field wants very short pulses to time-resolved dynamics in atoms and molecules. And of course we know from the Fourier transform of a very short pulse gives you a very broad spectrum, right? So it's centered at the same optical frequency, 470 terahertz, but the shorter the pulse in this time domain, the broader the bandwidth in the frequency domain. So what if we have a pair of pulses rather than a single pulse? If we have a pair of pulses, the spectrum from each pulse is identical, right? At least the amplitude of the spectrum. However, because of this time delay between the two pulses, there's going to be a linear spectral phase that's different from one pulse to the next, right? So in this frequency spectrum, you can think of one of them having a linear spectral phase with a slope that's proportional to this time delay. Okay? And because of that difference in the phase between the two spectrum, you get spectral interference fringes when you look at the combined spectrum of these two. So the spacing between these constructive interference peaks then is given by exactly 1 over the time delay between the pulses. Now, if instead of a pair of pulses you have a pulse train, you add more and more pulses together, these positions of constructive interference get narrower and narrower and turn into little delta function or comb teeth. Okay? And the spacing is exactly determined by that separation time or the repetition rate of the pulse train. That's sort of the simple basic picture of the frequency comb. And so these were very different tools initially between these two communities. But way back in, as early as I guess this was in 78, but in the 70s, Ted Hensch and colleagues started looking at these mode-locked laser sources for precision spectroscopy. And they've been using them for quite some time now. And so this was an interesting paper where they're looking at transitions in, I believe it was the sodium atom, and they're looking at the fine structure splitting in the upper state of the sodium atom. And they're using a picosecond pulse train from a dye laser. That in and of itself is a challenging experiment. But here's the energy level of some of the energy levels of sodium. Right? And it's this 4D state that they wanted to measure the frequency spacing. Okay? And they used a mode-locked laser to make a more precise measurement of that spacing. And one way to think of how they did it is to just say, well, they took this mode-locked laser and they took those comb teeth and they lined it up such that they excited the atom from the common ground state up to one of these two energy levels corresponding to the fine structure splitting. Right? And so once they had the repetition rate at the correct value, they could be resonant simultaneously with both of these energy levels. Okay? And then the repetition rate would tell you what the fine structure splitting was. That's roughly how they did it. Okay? It's a simplified picture of how they did it. But the idea was now that they could use these really fine comb teeth to measure the splitting of the fine structure and make a precise measurement of the value. Now this splitting, as they point out in the paper, was only about 1 gigahertz apart. And you could do this experiment by taking 2 CW lasers, locking them each to a transition, and just beating them at 1 gigahertz. Right? But what they were interested in doing eventually is to look at comparing bigger splittings. So for instance, they mentioned the hydrogen and deuterium isotope shift. Okay? This is around 168 gigahertz. And if you have 2 CW lasers separated back then by 168 gigahertz, it would be very hard to directly measure that beat frequency. So the idea proposed here is to use mode-locked lasers, picosecond mode-locked lasers, to connect large frequency intervals to compare transitions that are relevant for their experiments. Okay. So the concept idea has been out there for quite some time. So we started with mode-locked lasers. Then it was sort of interesting to see how it developed. Then the idea was, well, let's start with a CW laser. And groups such as Kurogi's frequency comb was used. This was in the 90s, but it was much earlier than that it began this work, where you started with just a single frequency laser, and you put on phase or amplitude modulation to create sidebands, to create a comb of frequencies that way. Eventually, you put this phase modulator in an optical cavity to extend the bandwidth of the comb. And then later on, people started using mode-lock lasers again, and then now more recently, we're using CW lasers again and using parametric generation to create the sidebands. Okay? So there's been a lot of work in this area since the late 70s to connect large frequency intervals. Now, in 2005, a portion of the Nobel Prize was given to John Hall and Ted Hench for the development of these optical frequency comb techniques. And if that was the whole part of the story, you might think, well, that's not too difficult. It's just a very simple Fourier transform relationship. What was the really challenging problem that these two solved? And the thing that was confusing before the turn of the century, really, and the problem that we wanted to solve was that, well, if you look at the pulses coming out of the mode-lock laser, are they really identical? You know, in the picture that I gave before, each pulse was perfectly identical, and it was just delayed in time by some time. But really, the pulses coming out from pulse to pulse don't necessarily have to have the same carrier envelope offset phase. So the carrier envelope offset phase can just be defined as the distance between the peak of the envelope and maybe one crest of this oscillation, right? Whatever that little phase difference is. And from one pulse to the next, that could be different. Right? The question is, well, do these things get so dephased inside the laser oscillator? That's just completely random, right? Because then you don't have identical pulses and this frequency comb washes out. And why would they be the same? So there was a lot of confusion there. To some people it was obvious, to others it wasn't, and now it's obvious to everyone. But at the time, there was no way to directly measure this. And so there was some uncertainty as to how well this frequency comb could really work over large intervals, and other questions related to that. Well, it turns out there's no reason these pulses have to be identical, because inside the laser cavity, the pulse travels at the group velocity, right? Whereas this carrier frequency travels at the phase velocity. So each round trip, there's going to be a slippage of this pulse envelope to the carrier frequency. So it certainly can evolve. The question is, could you detect it? And of course, in this field, if you can detect it, then you can stabilize it. Right? So that's really the problem they solved, was how to detect that carrier envelope offset frequency and to stabilize it. Okay? And we won't go into the details of that, but that's a problem that's been solved. And now we can generate these pulse trains where this phase evolution from pulse to pulse is stable. But now we do have this time-varying phase from pulse to pulse. There's a phase shift between them, and it happens at a period t. So now when you take the Fourier transform and you look at this comb spectrum, and in terms of the absolute frequency, you still have equally spaced frequency comb teeth, just like before, that they had been using for a while. But now you can determine, if you trace these little frequencies back down to 0, what the so-called offset frequency is. It's just phase evolution from pulse to pulse. So this so-called carrier envelope offset frequency is just the phase change between pulses divided by the repetition time. So this had a huge impact, because now not only could you link large frequencies with this comb, but you knew the absolute frequency of each comb tooth. I mean, that was the real significant change that happened with the development of the frequency comb. So now each one of these optical frequencies of the laser could be determined. It's some integer multiple times the repetition rate plus that offset frequency. Okay? And so if you had a CW laser and you're investigating a molecule or an atom and you want to know exactly what the optical frequency is for that system, 474 terahertz was hard to measure. Now you can simply count these microwave frequencies and determine what that optical frequency is with a very high accuracy. Right? Counting the repetition rate, you put that into a frequency counter, you get 12 digits out. And it wasn't much harder to measure the offset frequency or this beat frequency. So you generate a beat frequency between the CW laser that you want to measure and the nearest comb tooth. Okay? And you can control all these frequencies as well. So now if you have a very stable transition and you lock your laser to it, by locking your comb to that CW laser, and say you set the offset frequency to 0, now you transfer the stability of that laser across the entire spectrum of the frequency comb. And as you saw in that first picture, that frequency comb spectrum can cover the entire visible spectrum, the ultraviolet spectrum. So you only need one extremely stable laser source, and you can transfer it across the entire visible spectrum. And you can measure all these different optical transitions, both for comparison of fundamental theories, but also for a whole host of applications like in spectroscopy. I think the first real big impact, of course, that people heard about was the effect on developing atomic clocks based on these optical transitions, because now it was easy to measure optical transitions. And a lot of other applications we've heard about in a previous Colloquium speaker's talk, Nate Newberry, there's low phase noise microwave sources. Now you take that optical transition that has a very high Q, very high frequency, and you can take that stability and convert it to the microwave. and a whole host of applications. As far as the optical atomic clocks, just to give a simple picture of the components, you take your stable laser, you lock it to your narrow atomic transition. There's a feedback system that keep that laser tracking this narrow atomic resonance. And they've had this for a while. The problem is, how do you count that optical frequency? Well, now you just link it to your frequency comb, your mode lock laser, and you count the pulse repetition rate. And you multiply it by the appropriate integer, and now you know what that clock frequency is, hundreds of terahertz. So strontium atoms are one as far as neutral atomic clocks that have been studied. And we've been looking in the past couple of years at neutral mercury atoms, which have a very similar structure to strontium, but have some other interesting applications and some other potential advantages. But now let's turn this problem around. The initial impact was really in spectroscopy and optical frequency metrology. But now if we think about it in the other way, if we stabilize these frequencies or set them to 0, that also means that we can generate these waveforms with controlled electric fields. And we can also transfer the stability of the CW laser to these ultra-short pulses. Okay? So before the turn of the century, approximately, this field of ultrafast science and all the simulations, the light-matter interaction, we're really using pulses that sort of look like this, right? Very short bursts of light, but there wasn't a lot of talk about the carrier frequency, whether it was relevant or not. With the development of the frequency comb techniques, you could now stabilize that carrier frequency, and you gain access to this subcycle field. Okay? So the pulse durations were maybe 5, 10, 100 femtoseconds, but now you could really make use of this few femtosecond oscillation of the electric field waveform. And that really opened up this field of attosecond science. Right? A fraction of an optical cycle is on the order of attoseconds. Okay? And so a number of applications where you can really utilize this electric field at an instant of time, and you can use it sort of as a sweep of the electric field. So you can do things like, access the high field strength. You can synchronize multiple pulse trains, coherently add these pulses together to make a shorter one. That's been demonstrated. And I mentioned the subcycle control of ionization dynamics. Right? So experiments like this opened up that are really quite cool. You can send a very short pulse and intersect a gas jet where you're going to ionize the atoms. And then you have a detector on either side that detects the photo-ejected electron from that atom. But now you're using these pulses where you can arrange things, if the pulses are short enough, that only this oscillation of the field ionizes the atom. Okay? And so depending on the sign of this oscillation, you can kick the electron to the right, or you can kick the electron to the left. Right? This is something, a tool you never had before. And that's what the data shown here in this earlier paper shows. As they change the carrier envelope offset phase, the electron goes to the left or the electron goes to the right. Okay? So this really opened up, in fact, the field of femtosecond science changed to attosecond science at about this time, right? Because now you had access to these subcycle timing events, whether or not you had a single isolated attosecond pulse or not. So that's where things had been, and now so the idea is, well, why do we want to extend this to the vacuum ultraviolet? So we've been able to do this high-resolution spectroscopy in the visible region. But there's a whole host of interesting systems down here in the vacuum ultraviolet and the extreme ultraviolet where we don't have these very precise tools that we're enjoying in the spectral region. Right? So in this region down here, more or less, the majority of the spectroscopy and work being done is still dominated by these sort of Newtonian-era dispersive spectrometers, right? High-resolution spectrometers, but we don't enjoy the same precision measurements that we can do in the other spectrum. So the idea of extending the frequency comb from, this, say, a laser source here by high harmonic generation is to generate higher harmonics of that down into the vacuum ultraviolet and extreme ultraviolet. So this is a recent work showing harmonics of our fundamental laser pulse. And recently that we demonstrated that we're able to get on the order of tens of microwatts of power down at these wavelengths, down to 50 nanometers or so, which is where our grading cut off at the time. And I don't know if that sounds like a lot, but it's enough to do a lot of experiments, microwatts of power. And in this photo, you can actually see this is the ionization potential of xenon. It looks like some incoherent emission from the Rydberg states of that. But presumably, inside each of these little components, now we have this femtosecond comb structure, but that's something that we want to investigate. So what's interesting? Why go down to these wavelengths? Well, a lot of the fundamental atoms, and molecules, and ions have their first resonant transition in the vacuum ultraviolet. So a lot of the fundamental physics that you want to study will be greatly aided by being able to do precision spectroscopy in this region. So hydrogen, helium, helium-ion, a lot of these transitions are down in the vacuum ultraviolet for these same fundamental tests that I mentioned before. There's also a number of molecular transitions that are of great astrophysical importance by comparing telescope observations with Earth-based observations. Right? So we need more precise data for that. And one in particular, if I have time to get to it, we think we'll be able to measure Rydberg states. So Rydberg states are very high principal quantum number states, very near the ionization potential of the atom or the molecule. And in particular, molecular hydrogen would greatly benefit from a measurement of the Rydberg state because it would immediately improve the dissociation energy for that molecule. So I'll come back to that if we have time. And then there's all sorts of other crazy type of measurements one can do. One I find very interesting because we have access to it is the idea of exciting a nuclear transition in this case, thorium-229. So the idea here is that you take a VUV transparent crystal like lithium YCAF and dope it with this thorium atom. It actually it's really the only known low energy nuclear transition, and it's estimated to be around 160 nanometers. No one's directly observed it. And so we have colleagues that have built these doped crystals at UCLA. They're taking the advanced light source, and they're trying to coarsely locate these transitions. And if they do, then we'll be able to search for these with the VUV comb as well. At least that's the hope. So a VUV comb would also be a benefit in ultrafast science. These other experiments are running at hundreds of hertz, maybe kilohertz repetition rates. Right? If we have megahertz repetition rate sources, we could potentially improve the photon flux in all these different experiments that are being done. So, for example, these pump probe time-resolved experiments, these gas targets that are studied and used sometimes are very dilute, and especially if you use something like a supersonic gas jet to cool the molecule down. And in those cases, some of these experiments you integrate for hours or even days, and a lot of them aren't feasible just because of the signal to noise. So high flux sources would have a big impact there. Same with photoemission spectroscopy of condensed matter. There's a group right now hooking up a XUV comb for these type of measurements, because if a single pulse, so in these experiments you're going to photoionize electrons off of a metal surface. And if you take too many off each pulse, then you're going to have space charge effects that are going to affect momentum of those electrons. So what you really want is low energy pulses, but at a higher repetition rate. And then there's a host of other applications like coherent diffractive imaging that all benefit from these types of sources. So how do we generate it? So we'll finally get to that. So high harmonic generation, I think we've heard about this already in the colloquium, but just briefly, the idea here is that if we start with a single amplified pulse, so not a pulse train, usually you take a mode-locked laser, you select one pulse, and you dump the rest. And you amplify that single pulse to very high energies, and you focus it down into a gas jet so you can reach intensities that are high enough to ionize the atoms. And what comes out is a very coherent beam of light in the extreme ultraviolet. Right? Very high harmonics of that fundamental frequency. And so the model that's been used very successfully, the simple model to explain this, is the so-called three-step model. So initially you have, just pretend it's a hydrogen atom, and you have your electron bound in the Coulomb potential. And you apply this very intense electric field from the pulse. So within one optical cycle, you greatly perturb that potential, enough so that you can have this electron tunnel out. When the electron tunnels out, now it's in the continuum, and you can treat it as moving freely from the Lorentz force with the electric field of the pulse. Now the pulse oscillation changes sign. This electron that's been pulled out can reverse its direction and momentum. And as it comes back, it can scatter, hit the parent ion. And in some cases, it can recombine back to the ground state. And all the energy the electron gained in its journey can be given off as a high-energy photon. Okay, so that's the simple picture. And it allows you to really scale up to high energies, right? If you look at bound optical nonlinearities, you can't ionize anything. You can generate harmonics of the laser field, but you can only go up to certain energies, otherwise you ionize the thing. This isn't limited in that. This, you want to give as much energy to this free electron as you can and slam it back in and generate a coherent light from that recollision. That's a simple picture, but it requires these high intensities. So if we want to use that process to upconvert the light from a frequency comb, we need these high intensities and high energies. And so the way we approached that first back in 2005 was to take this coherent pulse train from the laser and store it inside what we call a femtosecond enhancement cavity. So this is just a passive resonator, passive cavity with nothing inside. And now we simply stabilize it to this cavity. But now there's 2 degrees of freedom to lock. Right? We have the round-trip time of the pulse, and we have the phase of the pulse. Okay? But when we control that right, and we can get a single pulse stored up inside this cavity and enhanced by a few hundred to 1,000 times. And so with this type of a source, we can trap a short pulse in this cavity that has the needed intensities for high harmonic generation and has kilowatt level average powers. So you can't buy a laser system that has 10 kilowatts of average power and 100 femtosecond pulses. If you do, we'll do it, and then all these other experiments will be easier. So this is a very unique source inside this cavity, and people have been using this for a lot of different applications as well. But it does work well for high harmonic generation. So the idea is to simply put in a gas jet at the intracavity focus and use the same process to upconvert this frequency comb. That was first demonstrated, as I said, in 2005 in Juni's group and at the MPQ in Germany. To actually there's a lot of difficulties, but one is to get the high harmonics of this fundamental light out. We had to put in some element like a Brewster plate. So the Brewster plate has no losses for the fundamental light, but down here at 50 nanometers, the index is different, and you can couple out like 10% of this EUV light. Okay. So the cavity itself back then looked something more like this. It's a ring cavity. Pulse is stored in here. It ionizes this gas jet of xenon, and harmonics come out over here, and it just continues to go around in this circle. And this is an actual beam profile of the 3rd, 5th, and 7th harmonic that's coupled out on a phosphor screen. So back then we were generating the 3rd, the 5th, and the 7th harmonic, and we thought, well, this is pretty cool. But of course, that's not many harmonics. The light's really not that far in the vacuum ultraviolet, and there's extremely low light power levels, okay? Picowatts probably. And so since then, we've done a lot to really improve these sources and to get to much, much higher average powers where we can actually start to do experiments with it. And so I would say that sort of these next generation XUV combs are better primarily because of two factors. One is the use of high power fiber lasers, right? Very efficient and quite affordable compared to high sapphire. Ytterbium fiber laser technology, where we can now generate average of 50 watts average power from a frequency comb before going into the enhancement cavity. Okay. And the other significant advance is that we have a much better understanding now of what's going on inside these cavities during the high harmonic generation process. So this is just a figure inside the laser cavity. This is a focusing mirror. So the laser pulse comes inside the cavity. It's focused down. This is the xenon gas jet that ionizes. This is the Brewster plate. So the fundamental pulse just passes through that, and the high harmonics are coupled out off of that. So let me talk a little bit about doing high harmonic generation inside these enhancement cavities and what sort of we've found the fundamental limitations to this approach to be. So as before I said, we start with this mode lock pulse train, couple it to the cavity. We're generating these harmonics. Now we have to keep the laser resonant with this cavity. And so that means we have to have the round trip phase shift for the pulse be some integer multiple of 2 pi. Right? Now when we turn on this gas jet, of course, I said we have this ionization process that's happening. And when we ionize the gas jet, the index of refraction changes. So there's a phase shift on the pulse. And so now the round trip phase for the pulse changes. We have the normal linear contribution, but now there's a nonlinear response inside this cavity. Okay. Now when this nonlinear response gets too large, then we run into problems. So sort of a rule of thumb for the maximum nonlinear phase shift we can have inside the cavity is pi divided by the finesse of the cavity. Well, that phase shift corresponds to when the resonance of this cavity shifts by about the fullest half max of the cavity. Right? It becomes a significant shift of the cavity resonance. So this is what we see, for example. So this is data that we see at 0 torr, that's the backing pressure. It means there's no gas inside the chamber. And as we scan the cavity or the laser through resonance, we see this very nice Lorentzian symmetric line shape. Right? It's just the resonance of the cavity. If we turn on the gas jet, and now we're ionizing the xenon, because of that nonlinear phase shift, this peak shifts due to the ionization of the xenon. And so we did a lot of simulations on this, along with you and Wright, to try and understand exactly what's going on and how big the effects were. And so we compared some numerical simulations with our experiment. And so you can see the plots agreed pretty well. And what we're seeing now is at different pressures inside the cavity for the xenon target, the nonlinear phase shift becomes more and more significant. And there's two main things that happen. First of all, the resonant frequency shifts, but then it also starts to decrease. Okay? So there's really two limiting effects inside these cavities. One is that there's a residual static plasma background. So when that pulse goes through the gas jet and ionizes it and it comes back around and some of that plasma is still there. It hasn't all dissipated, recombined, or moved out of the way. And so in the steady state, you get this background plasma that's just sitting there. But you also get the dynamic ionization of the gas jet each time you go through, and that fast-changing phase chirps the laser pulse. And then you can no longer constructively interfere with the incident pulse. And so you get a decrease in the peak enhancement or buildup in the cavity that you can get. So those are the two limitations to the plasma that's going on in there. Now the curves I showed are when you scan across the cavity resonance in one direction. Now if you know anything about resonant systems and nonlinearity, you know they're going to be bistable. So if you scan in the opposite direction, you see a different curve. So here's the blue curve is the transmission under vacuum, and the red and green are when you scan in different directions. Okay? So this is another technical problem with this, is that when we try and stabilize the laser to the peak resonance of this cavity, because of the bistability of the cavity, it can quickly unlock or oscillate. So a lot of bad things happen. So it causes some problems. So just to summarize, it limits the peak intracavity intensity. It creates this bistability. And also, all that extra ionization is going to mess with the phase matching requirements for high harmonic generation. Okay? So we don't want that around. And so we first really were able to quantify this a bit back in 2011, and the Gilla group did as well, as being a fundamental limit for intracavity high harmonic generation. But what we were really looking at is a comparison with our numerical simulations and getting an idea for what the shift was, but we couldn't really see the ionization in great detail. So we come up with a new technique to really look at the ionization in real time and see how it's shifting and immediately what the background level is. And so we have a new technique then for this time resolving these ionization events, but it's also used for measuring any optical nonlinearity with a very high precision. So our goal was to get a better physical understanding of this plasma dynamics to try and improve it. And in order to do that, we really have to do a pump probe experiment inside the cavity, which means we need to get two pulses inside the cavity. So the experiment looks something like this. We have our enhancement cavity. And if we look at the incident laser spectrum shown here in black, if we line up everything perfectly, we can couple in most of the laser spectrum. Okay? So we want a very broad spectrum coupled in because that means we can store a very short pulse inside the cavity. Now if we detune the repetition rate of the laser, now it's not perfectly matched with the cavity. Right? The pulse comes around and they don't perfectly overlap. And so if we detune it by 50 hertz, for example, then the spectrum that we can actually couple into the cavity is very, very narrow. And our pulses will be very, very long. However, if we detune it by just a little bit, say 4 hertz, we've seen that we can still couple in 100 femtosecond pulses. So there's a little flexibility in the detuning. So what this means then is that we can in fact couple in two independent lasers with a slight detuning. And so that's what we do. So this new measurement technique goes something like this. We have the usual high power frequency comb coupled to the cavity, and it's generating this ionization each round trip, ionizing the gas jet. Now we have a second comb. We turn the power way down so it acts as a probe to first order. And this one, in this case, is going in the opposite direction inside the cavity. Okay? And now we can make the repetition rates identical or slightly different so that after this pump pulse goes through and ionizes the gas jet, the probe arrives at a slightly different delay each round trip. So we're scanning the delay for the probe relative to the pump. Now, the cavity in this case does two things. It gives us the high intensities for the pulses, but any small phase change that the probe sees is translated into a frequency shift of the cavity. So we're using it to sort of amplify the phase shift due to the plasma. And now the probe is going to sense a plasma at a given time delay. And depending on how the plasma evolves in time, it's going to get a different phase shift. So this is what we see in these type of experiments. So this is a, let me go to this one first, because this is all very recent data. But this one's calibrated in terms of the phase shift. So this is a function of the probe delay. And what we're measuring is the phase shift that the probe sees due to the residual plasma. Okay? So at 0 probe delay, that corresponds to when the pump and the probe go into the gas jet at the same time. The pump creates a strong plasma, the probe gets a strong phase shift, and the phase shift goes up here to like 5 milliradians. Now the probe is going to be delayed each round trip, and as the probe is delayed, the remaining plasma that it sees is decreasing, and it goes down to some value. But then it overlaps with the pump again, and it jumps back up. Okay? So we're able to see in real time the ionization of this plasma, and now we can do things like vary the gas pressure. So you can see that 0 is down here, and at these high pressures, we're generating this much ionization in a single pass, but we have this large background plasma level. So for the first time, we can really see these ionization dynamics inside the enhancement cavity. From this phase shift, then, we can calculate what the corresponding electron density would be inside the cavity. And here we looked at, we just normalized, this is a different data set, but we normalized the curve for different backing pressures. And what we can see is that at higher pressures, in this case, 400 torr, the decay is faster. And we have a lower background plasma level. Those are the type of things we want, because that's what's causing the problem. This would make sense, and this is sort of preliminary data, so we're still checking everything. This would make sense because at higher pressures, everything's moving through the interaction region quicker, and so it just may be getting out of the way. Right? So that's a good thing. Another set of experiments we can do is to keep the backing pressure, the gas target, the same, and vary the intracavity power. So now we're ionizing more each round trip as we increase the power. So we go on the order of 2 to 5 kilowatts, and we'll ionize more. But we've normalized everything to 1 so you can see the fraction of plasma remaining. And what we've seen is that for the highest intracavity powers, the decay is faster. Right? So the only way we can explain that is that if it's due to 3-body recombination. The higher the density, the quicker they recombine. But no one's been able to look at these very carefully before to know exactly what affects the plasma evolution inside these cavities. So now that we can see it clearly, we can start looking at things that might affect it. So we can look at different nozzle geometries. We can then try and increase the gas velocity by seeding it, and different ideas like that. But this is really, since this is really a fundamental limit to these XUV frequency combs, the fact that we can see these ionization dynamics, hopefully we can minimize their effects and greatly improve these sources as well. We can also measure other optical nonlinearities inside the cavity. These pulses go in opposite directions, and each round trip they meet at a different place inside the cavity. Right? So, and we can make them stop and always meet at the same place. They're completely phase coherent. So we can zoom in, for example, on that Brewster plate and measure the nonlinearity of that. Or we could potentially zoom in on the mirrors, because these mirrors are right at the damage threshold because the powers are so high, and measure the nonlinear response of these dielectric mirrors. Those are things we haven't done yet, but these are things that we can now do with this system. Now, there's a lot of other nonlinearities and problems in these cavities. So what about spatial effects of this plasma evolution? We're really probing sort of the average on-axis density of these. And what about thermal nonlinearities in the cavities? These are also limitations. So we've sort of extended this probe by incorporating higher-order spatial modes in the cavity to get at what's going on. So just as before, we have our femtosecond pump beam generating a plasma. And now we have our probe beam. It can actually be, in our initial experience, a CW laser, but we'll eventually do it with femtosecond laser. But for our probe beam now, we're going to make use of higher-order spatial modes. Okay? So, for instance, if we use, instead of the lowest-order mode, a higher-order mode like the 0-3 mode, as a probe beam, this is not going to overlap as much with the plasma that's generated by the pump beam. Right? So we plotted here the plasma that would be generated by the lowest-order beam, and the overlap that a 0-3 beam would see with that. Okay? And so if you then calculate, based on that spatial overlap, the phase shift of a probe beam with a 0-3 mode versus a 0-0 mode, it means it's only going to see about 12% of the plasma. in that case. And if we had a much higher order spatial mode, it would be less than 1%. Okay? So now we can compare, for the probe beam, the difference between the 0,0 and the 0,3 mode. Right? So the first order, the 0,3 mode doesn't see the plasma, but it would see everything else. The 0,0 mode would see the plasma phase shift. So we split the probe beam up into two beams. We have to use an acousto-optic modulator so it can track the changing resonance for one beam. And we couple one probe beam with the 0,3 and the other probe beam with the 0,0. And so we can look at things like this. We have two curves here. One is when there's no gas jet on, just the empty cavity, and the other when there's 100 torr backing pressure in the cavity. And we look at, this is the phase difference between the 0,3 mode and the 0,0 mode as a function of the intracavity power. In this case, we only went up to 2.5 kilowatts. So now we see a lot of different interesting things. Down at very low intracavity power, we're not ionizing anything. We look at these two curves with the gas on, gas off, and we see there's a difference. Right? On this curve, it looks small, but it's actually a very significant difference between these two. This is just a phase shift due to the fact that it's not a uniform gas jet. There's variations in the gas jet. Maybe it's a Gaussian profile. And so the 0,3 beam is sampling the gas jet differently than the 0,0 beam. Okay? So by using a lot of higher order modes, we can sort of get at the distribution of the gas jet. Okay? Then as we turn up the intracavity power, even with no gas on, so there's no ionization going, the difference between 0,0 and the 0,3 mode changes dramatically. It's like the biggest change that we see, actually. Right? And the reason for this is due to the thermal response of the cavity mirrors. And we're operating with kilowatts inside of these cavities, and so if we don't use highly specialized mirrors, they just burn right away. But even with the best mirrors we can get, there's going to be a strong thermal effect. So the radius of curvature is going to change slightly, and that's going to change the round-trip phase shift for the 0,3 mode differently than for the 0,0 mode due to the GUI phase shift difference. Okay? So we see that thermal deformation by just looking at this curve and seeing that it's the same whether we have the gas jet on or gas jet off. And we can model this and come up with very good agreement that this is due to thermal effects in the cavity mirrors. And so we can see that for the first time as well. And then at very high intracavity powers, we see the difference that we were monitoring before, the difference between whether we're ionizing the gas jet or whether we're not. And so it's this difference here that tells us that plasma phase shift that we've been measuring. But it also tells us that it's a localized phase shift due to the plasma and not due to a lot of other effects that it could be due to. Okay, so the last thing I want to go on and talk about then is going on and moving forward and using this for experiments in the vacuum ultraviolet and extreme ultraviolet. And if I can get to it, I want to talk about the following. One is the possibility of measuring Rydberg transitions and molecular transitions in general, and a molecular hydrogen is one that we should be able to do, although it would be very challenging. And now there's a challenge with doing direct comb spectroscopy with molecules or Rydberg states. One is that we don't have a single frequency laser. We have this dense comb structure. And the other is that a lot of the spectra could be very closely spaced, so it's going to be hard to isolate one comb tooth to excite one transition. And the solution to this problem has been solved in the infrared already, and we heard a little bit about it recently, this idea of dual comb spectroscopy. And I'll tell you where we're at with that. But I found this paper a while ago that I thought was very interesting for a number of different reasons. And so why is molecular hydrogen interesting in this case, and what can we do with it? So in this case, this paper was about a hydrogen molecular ion, but the principles are the same. And the authors are actually from here in the physics and here in the Optical Sciences Center. And maybe some of you know some of the other authors, but I certainly recognize Bill Wing and, of course, Willis Lamb on this paper. And this was in '76. But it was an interesting paper because they were measuring molecular hydrogen transitions. And they pointed out that if the experimental measurements and the theory are good enough and get to a sufficiently high level of accuracy, then eventually the correspondence is going to be limited by certain fundamental quantities, like the electron to proton mass ratio. Okay? So if we can make precise enough measurements in molecular hydrogen and the theory is good enough, one can improve the value and the knowledge of fundamental quantities like the electron to proton mass ratio. Okay? The other thing I found interesting in this paper was another name. It says this was published without review at the request of Peter Franken, who's the former director here. And so I don't think they do that very often these days, but that was certainly a nice way to get it through quickly. And we could ask Tom if he can do this for us. Okay. Now we know. It's worth asking. So this idea, of course, has been around. And the real leaders in terms of precision measurements of molecular hydrogen is a group by Merck and a theorist, Wim Ubach, and others. And this is just one example of a recent paper they have where they showed sort of the history of measurements of the dissociation energy of molecular hydrogen. Not just the energy levels, but what's the ionization potential where you just dissociate this molecule. And this goes back to 1932 up to the present day. And the uncertainty decreases by orders of magnitude. Now, so the 100 kilohertz level is sort of where the theory is limited at the moment. But they've just improved that. And it's really, you have to get down to the 10 kilohertz level before you would start to be limited by the electron-to-proton mass ratio. So order of magnitude off, but feasible. Now, right now, what's the experimental side limited by? The way they do the measurements, very briefly, is you start with the ground state of the molecule. And there's a large gap up to these very high principal quantum numbers, the Rydberg states, that they can't span with current laser sources. So they look at stepwise excitation through intermediate states. Okay? And when they get to this high Rydberg state, then there's another method that is used to take it up to the ionization level. Okay? But it's this gap right here that's currently limiting the precision of these measurements at the megahertz level. Okay? So if you could measure directly from the ground state up to this state, it's known that you would immediately dramatically improve this measurement. Okay? And that's exactly the type of measurements we think we can do with these XUV frequency combs, except for this problem of the congestion of the spectra. Okay? So the challenge, as I just said, is the following. If we have an isolated narrow transition that we want to measure, then direct comb spectroscopy is pretty straightforward. Right? We send the frequency comb, the XUV frequency comb, through the gas jet that we're trying to, full of molecules that we want to study. And here's our comb teeth. And as you scan this tooth of the frequency cone through that resonance, you can cause the molecule to fluoresce, for example, and you can detect that fluorescence. Okay? This experiment has recently been done or demonstrated by the Giller group in transitions in neon and argon. Okay? But these type of systems are relatively rare. You need a very narrow transition, and it has to be an isolated transition. Otherwise, you'll end up with this situation where you have multiple transitions that overlap with multiple comb teeth, and the width of these transitions may be too large. So how would you do it in this case? Well, this is where this technique of dual comb spectroscopy solves the problem, and it's been demonstrated in the infrared portion of the spectrum. And we heard a little bit about it from Nate Newberry from NIST a couple weeks ago. So the basic idea is this. You need a second phase-coherent frequency comb to serve as sort of a local oscillator for your probing frequency comb. You send your probe comb through the gas jet just as before, and now you overlap this second comb with it. The second comb has a slightly different spacing for the comb teeth. Okay? So in the frequency domain, the picture is this. Each tooth of the probing frequency comb has a heterodyne beat note with this reference comb. Okay? But the heterodyne beat note for each comb tooth is slightly different. So you measure this beat frequencies. You have a whole comb of beat frequencies for each comb tooth. And what you see then, and this is data from the NIST group, this is the broader spectrum, and when you zoom in, you can see these individual heterodyne beat notes. Each one corresponds to a comb tooth of the probe laser. And if you have a very broad transition, that's okay, because now you just see how it absorbs all those different comb teeth. If you had a very narrow transition, you could just scan one comb tooth across it. And if you have a complicated molecular spectrum, and it's not the best image, but if you look in here, there's little notches in this that correspond to multiple molecular transitions. So this was done at 1.5 microns. Okay? Our goal, our plan, is to extend this dual comb technique into the extreme ultraviolet so that we can study a broader range of systems, like molecular transitions and Rydberg states. There you go. And we would also be able to see for the first time individual comb teeth in the vacuum ultraviolet and extreme ultraviolet. So the current results where we're at right now, we've developed not one but two of these 50-watt ytterbium fiber frequency combs, and they're phase coherent with each other. So we can do this initial experiment where we take the pulses in the infrared, phase lock together, we overlap them. In the time domain, you see this sort of cross-correlation signal, and you take the Fourier transform of that to get the spectrum. Now we can see the individual comb teeth of our laser in the infrared. Okay? And what we're working on now is to upconvert these combs into the vacuum ultraviolet and see if we can see for the first time individual narrow frequency components in the extreme ultraviolet. We've done some initial experiments on this using the single enhancement cavity, because this is what we were actually using for those pump probe measurements. But now we put the two combs in the same direction, and we have this delay between them. Now remember, we can make that delay be any length we want, and we can make these pulses, the delay change in time by giving them a slightly different repetition rate. So we have a precisely controllable delay between these two pulses, and they both go through and they each generate high harmonics, and then we can still get that same interference signal from this pulse train. Okay? So now we have pairs of VUV, XUV pulses with a controllable time delay, where in principle we should be able to do this type of spectroscopy. There's still a lot of problems with this, but we're sort of in the act of working on that right now. But it certainly looks like it's going to be feasible. So that's about it. I told you a little bit about the high-power laser systems we're using to develop this dual comb intracavity high harmonic generation. That data I showed you was really just for the third harmonic, so it's not quite as impressive, but it'll be much more interesting when we can do it for the 19th harmonic, right, down the extreme ultraviolet, which we've already generated, but not with dual comb system. We had this new dual comb intracavity pump probe measurement that we used to monitor the ionization dynamics in the cavity, but we think it has a lot of other applications for measuring optical nonlinearities. Because compared to other techniques, we have microradian phase sensitivity with extreme nonlinear optical intensities, whereas if you look at others, it's usually limited at the milliradian level. And then we also use these higher order spatial modes now to differentiate the linear and nonlinear response of the cavity. So that's where we're at today, and this is the team that's in the lab that's done all the work on this. So, thanks.